Hello everyone, welcome to Unit 9 of online course on probability distributions. So far we have discussed various aspects with respect to binomial distribution, its definition, different properties, a probability generating function, moment generative function, cumulative generative function, additive properties, etc. Now, we are going to discuss certain applications of binomial distribution in different fields by giving some examples corresponding to the fields of our discussion. As you know, binomial distribution is actually applied when we have two situations, when we are considering a random experiment, and for that random experiment we have only two outcomes, and that we call it as success and failure. So, whenever we have a experiment or whenever we have an event that is divided into two types, that is having certain attribute or do not possess certain that attribute. Such classification we call it as dichotomy, and let the proportion of individuals having such attribute in the population be P. Suppose these are given to you, then we are applying the binomial distribution. And an example, when we are considering in a population, suppose population is divided into two classes, literates and not literates, or smokers or non-smokers, or male and female, or defective and non-defective. Suppose the population is divided into two classes of like this, literate or not literate, smokers or non-smokers, male or female, etc. Then we are finding the probability of getting x number of successes. Successes may be in the case of literate or not literate, suppose number of literates is our success, and that probability function is actually probability of x is equal to x, n c x, p power x, q power n minus x, x is equal to 0, 1, 2, etc. up to n, and q is equal to 1 minus p. So, that is whenever we have a population, and for that population the events are classified either by success or failure, or defective or non-defective, or male or female, or smokers or non-smokers like this, then we are applying binomial probability to calculate probabilities corresponding to certain events. And now we are giving some examples where we are applying binomial distribution for finding probabilities. Consider this example. It is known that any item produced by a certain machine will be defective with the probability 0.1. Now, the question is, what is the probability that in a sample of 4 items, none of them are defective, and second is at most one will be defective. So, consider this question. This is an example where we are applying the binomial probability distribution. Why? Because the item produced by certain machine will be defective. So, that means second case is non-defective. So, items are classified as defective or non-defective. So, there are two events alone, defective and non-defective. And what is given again? The probability of getting defective outcome is given as 0.1. And then the question is, what is the probability that in a sample of 4 items, one of them are defective? and at most one will be defective. So, here what we are doing, suppose the classification of this defective items and non-defective. And suppose you let us define the random variable x as number of defectives, number of defectives, number of defectives. And what actually you are given that a sample of 4 items are selected, sample of 4 items are selected. So, that means n is given as 4, n is given as 4, and probability of given, again you are given probability of getting defective is 0.1. So, probability of getting defect is 0.1. So, number of items selected is 4, and suppose you are defining x as the number of defectives, and let p be the probability of getting a defective, that is 0.1. And then you consider a problem. The problem is, what is our question? None of them are defective. So, none of them are. So, what is our problem? The probability of none of the selected items are defective. None of them are defective. This is our problem. You have to find what is the probability of none of the selected items are defective. That is, corresponding to the random variable definition, x is defined as number of defectives. So, this is probability of none of them are defective. That means probability of x is equal to 0. And how do you find the probability of x is equal to 0 here? And that is, if x is a binomial random variable with a parameter n and p, we have the probability of x is equal to x, that is probability mass function, general expression we know NCX, p power x, q power n minus x. So, what is our probability of x is equal to 0? That is NC0, p power 0, q power n minus 0. Or generally, this is always, you remember, the probability of x is equal to 0 is always equal to q power n, that is equal to, earlier we have the n is equal to 4 and p is equal to 0.1. So, q is 1 minus p, that is 1 minus 0.1, 0.9. So, it is 0.90 power 4. So, this is our probability of x is equal to 0. So, this is a problem where we are applying binomial probability, because we have a random experiment of selecting items, and that items are maybe defective or non-defective, and probability of getting a defective is already given as 0.1. So, if it is so, what the probability of getting 0 defectives when we are selecting 4 items is 0.90 power 4. And again, the next is at most one will be defective. What is the probability of getting? At most one will be defective. At most one will be defective means probability of at most one of them will be defective. Out of selected items, at most one of them will be defective. So, if you transform this statement to random variable way, random variable x, this is at most 1, that is x less than or equal to 1, maximum is 1. And the meaning is, this is equal to probability of x is equal to 0 or 1, or that is probability of x is equal to 0 plus probability of x is equal to 1. Apply the binomial probability mass function here. It is q power n. Probability of x is equal to 0 is q power n. That is 0.90 power 4. And probability of x is equal to 1 means 4c1 p power 1. That is p power 1 means 0.10. Q power, that is 0.90, power 4 minus 1, that is power 3. So, this is equal to 0.90 power 4 plus 4 into 0.10 into 0.90 power 3. And simplifying that expression, this is equal to 0.9477. So, see, when we have a random experiment of this selecting items that are classified as either defective or non-defective, and the probability of selecting defective is given as 0.1, then probability of at most one defective is obtained by this expression, and simplifying, this is the value. So, this is an example where we are applying binomial probability. Consider another example. It is regarding an example in the medical field. The lifetime risk of developing pancreatic cancer is about 1 in 78 people, 1 out of 78. That is approximately 1.28%. Suppose we randomly sample 200 people and let x be the number of people who will develop pancreatic cancer. So, this is an example in the medical field. You are given developing pancreatic cancer is about 1 in 78. So, P is given to you. Suppose P is the probability of developing a pancreatic cancer, and that is given as 1 out of 78. And we are selecting people from a sample of 200, that is n is equal to 200. N is equal to 200. If it is, first of all you have to write what is the probability distribution for x. Here you see you have a sample of 200 people and we define the random variable x, that is x is the number of people who will develop pancreatic cancer, x is the number of people who will develop pancreatic cancer. So, if it is, what is the probability distribution of x? And see what is the probability distribution of x. So, you are given n is equal to 200 and p is the probability of developing pancreatic cancer, that is 1 out of 78, and that value is equal to 1 out of 78 is given to you. And so, if it is, what is the probability of, the question is the probability distribution of for x. So, probability distribution of x is f of x is equal to NCX p power x q power n minus x. Here n is 200 Cx p power x 1 out 78 power x, and 1 minus, so 77 divided by 78 power 200 minus x, where x have any value from 0, 1, 2 etc. up to 200. So, this is the probability distribution function of that random variable. See here n is very large here. So, we can approximate that probability distribution to Poisson distribution that we will discuss in the next session when we are discussing Poisson distribution. Okay. So, if we are applying binomial distribution, here n is equal to 200 and p is equal to 1 out of 78, and if it is the f of x, the probability distribution of x is n c x p power x q power n minus x. And second part of this one, if it is what is the mean of the random variable and the standard deviation of x. So, when you have see n is equal to 200 you are given and p is equal to 1 out of 78, and suppose x is the number of people who affected pancreatic cancer, then x follows binomial with 200 and 1 out of 78. This is our distribution. If it is, what is the mean of x? Mean of x, we know it is our expectation of x, and for a binomial distribution we discuss the mean as the product of the parameters n and p, and that is 200 into 1 divided by 78. So, this is the mean of the random variable. Similarly, standard deviation, and we know the standard deviation is the square root of the variance. So, if we have the variance of x and variance of x is our NPQ for a binomial distribution, and if x is the binomial random variable, variance is equal to NPQ, and standard deviation is the square root of that variance positive value, that is square root of NPQ, and that is equal to square root of 200 into 1 out of 78 into 77 divided by 78. So, this is our mean and variance. So, the advantage of this is, if you define, so whenever we have in the medical field we have affecting pancreatic pancreatic cancer patients and not having the pancreatic cancer. So, we have the two dichotomy here, that is pancreatic cancer or not having pancreatic cancer. Okay. And x is the number of people affected pancreatic cancer, and suppose you are given p, the probability of affecting the pancreatic cancer is 1 out of 78, and we have a sample of 200 people, and if it is if we are applying binomial distribution, then that random variable x follows binomial with 200 and p as 1 out of 78. And if it is available to you, then it is very simple to calculate the mean and the variance or whatever be the parameters that we require for that. That is, mean is equal to expectation of x, that is equal to NP, and the standard deviation or square root of the variance is equal to root of NPQ, and that can be calculated like this. And find the probability that at most 2 people develop. This is another question. What is the probability that at most 2 people develop pancreatic cancer? So, that also is available from this expression, at most 2 people. At most 2 people means x less than or equal to 2. So, that is probability of x less than or equal to 2 means probability of x is equal to 0, 1 or 2. That is sigma from x is equal to 0 to 2 NCX, that is 200 CX 1 divided by 78 power x, 77 divided by 78 power 200 minus x. Simplifying this expression, you will get the probability. So, since n is large, we can approximate this case to Poisson distribution, but when we are applying binomial distribution, this is the way we are calculating probability. So, another example, suppose an example regarding the tossing of coin. Already we discussed several times the tossing of coin experiment, and here that we are tossing a coin 12 times. So, that means n is equal to 12 and tossing the coin. So, the probability of getting, suppose x is the, you define, first of all you define the random variable. Here you are tossing a coin. The question is, in how many cases one expect 8 heads and 4 tails. Suppose we define x as the number of heads, then x can have any value from 0 to 12 and corresponding f of x, this is equal to ncx p power x q power n minus x. And so, this is we know n is given to you as 12 and p is the probability of getting head, that is 1 by 2. If it is, our f of x is 12 c x p power x, that is 1 by 2 power x, q also 1 by 2 power 12 minus x. So, when p and q are equal, this expression reduces to of the form 12 c x 1 by 2 power 12, because combining get 1 by. So, this is a probability mass function of x random variable, where x is the number of heads obtained when we are tossing a coin 12 times. If it is, our question is in 256 sets of such experiments. And so, what is the case? So, how many cases one expect 8 heads and 4 tails. So, if that is the situation, first upon you find what is the probability of x is equal to 8 heads and 4 tails, that is automatically out of 12 tosses of a fair coin, if we are getting 8 heads, then there will be 4 tails. So, probability of x is equal to 8 we are calculating, that is 12 c 8 1 by 2 power 12. So, this is the probability of getting 8 heads and 4 tails. So, then the question is, in how many cases of 256 sets of such experiments? So, that is, we are repeating that in 256 times. So, what is the expected frequency? The question is here, expected frequency, expected number of experiments out of 256 experiments, in which there are 8 heads and 4 tails are obtained. So, that is equal to n into that probability. So, that is n is 256 into the probability here is 12 c x 1 by 2 power 12, and this is simplifying 1 by 2 power 8 and 256 cancels. So, sorry, 12 c 8 1 by 2 power 8. So, that is actually 12 c 8. So, the question here, out of 256 sets of tossing 12 coins at a time, in how many cases one may expect 8 heads and 4 tails is obtained as, that is 12 c 8. This is the number of cases in which there will be 8 heads and 4 tails out of 256 sets. Suppose a manufacturer knows that 5% of his products are defective. If the products are sold in boxes of 10 and guarantees that not more than 2 will be defective, what is the probability that a box will fail to meet the guaranteed quality? So, the question here is, a manufacturer knows that 5% of his products are defective. So, here also the classification is defective or non-defective. So, either defective or non-defective. And the probability from the previous knowledge, the manufacturer knows that 5% of his products are defective. So, P is equal to 5%. That means probability of getting a defective is 5% or 0.05. So, X is the number of defectives. Our random variable defined as X is the number of defectives. And the question is here, if the manufacturer selling the products in a boxes of 10, and so that is n is equal to 10. So, n is equal to 10 here. And so, the probability mass function here, so you are given X is equal to number of defectives. We define the X as number of defectives and n is equal to 10 and P is equal to 0.05. So, the probability mass function f of x, that is probability of x equal to x, that is 10 Cx, 0.05 power Ex, 0.95 power 10 minus 6, where x is equal to 0, 1, 2, etc. up to 10. So, this is the binomial probability mass function of this particular random variable. And just note what is our problem. The problem is, suppose if the products are sold in boxes of 10 and guarantees that not more than 2 will be defective, what is the probability that a box will fail to meet the guaranteed quality? Actually, the manufacturer guarantees that not more than 2 will be defective, not more than 2 will be defective. What is the probability that a box will fail to meet the guarantee? Fail to meet the guaranteed quality means our prop X is greater than 2. So, the manufacturer is actually claiming that guaranteed that not more than 2 will be defective, not more than 2 will be defective. So, when the guarantee is failing, that the number of defectives is larger than 2. So, that is we are actually, the question is to find what is the probability of x greater than 2. What is the probability of x greater than 2? That is same as if you are finding the complement part, 1 minus probability of x less than or equal to 2, or that is 1 minus probability of x is equal to 0, 1, let me write, probability of x is equal to 0 plus probability of x is equal to 1 plus probability of x is equal to, or that is equal to 1 minus probability of x is equal to 0, you know, it is cube power n, that is 0.95 power 10. Probability of x is equal to 1 means 10 C1, 0.05 into 0.95 power 9 plus probability of x is equal to 2 means 10 C2, 0.05 the all square, 0.95 power 8. Simplifying this expression, you will get the probability. So, this is the probability that the guarantee will fail. So, in such situations, that is in the case of IT field, in the case of management field, in the case of medical field, suppose the random experiment or the events are classified as either by success or failure or defective or non-defective or male or female, we can apply the binomial distribution to find the probabilities. And if the probability values are obtained, then other parameters or other characters of the distribution or the system or can be obtained. So, we can do any problems regarding finding the probability values of such situations using the binomial distribution. So, we will discuss more applications and problems in next session. So, with this we wind up this session. Thank you for hearing this topic. Thank you.